This is very much a short introduction to DSLT. There's a short introduction at the beginning into the whys and wherefores of SLT and a recap of what we've done with the light trial and why SLT and why the light trial. And it's just it's really just a short introductory thing. I think a lot of the interest in this when we've had these discussions in the past has been around the questions and some of the debate that it fosters. So by all means, give us the 10 minutes to have a chat, and then we can start to have a hopefully a more interesting debate on the DSLT and how it may fit in, some of the technicalities about the DSLT actual laser delivery, if that's what you would like, or the energy delivery, or really just where it fits into my practice. So whatever you prefer. Now, just to recap, and it is something that is said so often that it's easy if you're not careful to skip over it, but I think it is worth reminding us all what it is we are talking about with SLT of any kind and true SLT and true SLT energy delivery. There was a very interesting discussion earlier on in the Academy meeting with myself and Mark Latina, recapping the history of SLT over the last 20 years. It got FDA approval in 2001. It then took another 18 years before we had a sufficiently robust randomized controlled trial that changed the practice of National Institute of Clinical Excellence in the UK and changed the practice of most British glaucoma specialists. And in that time, other lasers have been put on the market, other lasers have been talked about. None of the other lasers that are out there are truly selective, because the critical science that underlies the choice of parameters for any form of true SLT laser, whether it's direct SLT or whether it's gonioscopy delivered SLT, is the 3 nanosecond pulse duration, which is shorter than the thermal relaxation time of the melanin, which means that you don't get thermal spreading, so you don't get heating and cooking of the tissues. Now, that was based on Mark Latina's work over 10 years of in vitro and animal model. He used owl monkeys for a lot of the time. He spent many years trying to damage trabecular meshwork, which is a story that's sometimes not realized, and then realized that with this, actually, although he was getting absorption and selective absorption of these pigmented tissues, that in fact they'd invented a treatment for it rather than an animal model of glaucoma. The actual wavelength is because you get the 532 nanometers, and the frequency doubled YAG 532 nanometers is so that you get a peak absorption in the melanin, and you get good melanin absorption of the melanin granules within the trabecular meshwork cells. 400 microns for the original laser was just a practical, easy to deliver large spot size that gave you the right sort of energy density to cover most of the TM, which is not a problem that we have with DSLT. And then they used fine bubbles as an endpoint, but that was in the original laser, and that was simply so that you knew that you were doing something, so that you could see something. There's no evidence that that's actually any better or worse than less energy that you can't see. But the selective nature of the laser compared to the thermal cooking energy of other lasers, pattern-delivered lasers or pattern scanning lasers, and the original argon laser, means that you don't get contraction of the meshwork, you don't get contraction and coagulation of the trabecular meshwork beams, and that means that it can be repeated, and it also means that it has a stimulatory effect on the trabecular meshwork cells and the nests of probably on the nests of stem cells that sit there at the Schwab's line area, and there's good evidence that those stem cells are stimulated to reproduce, and then they repopulate the trabecular meshwork. This obviously generated our interest in the light trial, and the light trial was a comparison between primary SLT versus primary drops, and in 2019 published that we were able to achieve at 3 years, 78% of eyes were drop-free and still controlled. At 6 years, we still had 70% of eyes independently controlled at pre-specified eye-specific target pressures defined by severity and starting pressure, without medication. So 70% of eyes could still be controlled for their glaucoma without medication. And that included pressures in the normal pressure range, that included normal pressure glaucomas right across the pressure range. We weren't pre-selecting for high pressure disease. And of those, round about half have been able to do that. Of those that were controlled, around about half, just over, were controlled with just one SLT. So what we have is a third of patients needing drops, a third of patients being controlled on one SLT, and a third of patients needing more than one to achieve a greater than 2/3 pressure of patients being pressure controlled at the end of 6 years and still being controlled thereafter. It didn't drop. They're not falling off the end of then and needing meds at 6 years. Some of these are going on right the way up probably to 10 years and beyond. And there's a whole host of subsidiary studies which we've published since then that the SLT could be repeated successfully and that it had independent visual field preservation above and beyond the absolute effects of intraocular pressure because the laser arm did better than the drops arm. So there are a number of different aspects that we looked at to show this better pressure control. There was less disease progression, there were fewer trabeculectomies, and there was a small difference in the rates of phacoemulsification. But this was the sort of headline results out to 6 years for the light trial looking at SLT. And the mechanism of action, as I said, it stimulates the stem cells to reproduce, but it seems to have a short-term inflammatory response as a cytokine release, recruiting macrophage monocytes into the trabecular meshwork, and all of that leading to a short-term increase in Schlemm's canal endothelial cell conductivity, which increases outflow. But then there's also this secondary repopulation, proliferation of cells within the trabecular meshwork, and that seems to give us a reset of the trabecular meshwork tissues itself. So there's not just a short period of change in tissues, but there's a long-term change such that, as Anders Heil said many years ago, some patients will have one SLT and be controlled for years. He had patients with pseudoexfoliation who had one laser trabeculoplasty controlled for 10, 15 years with no intervention. Now, those are uncommon. Most people, the SLT wears off, the disease process catches up with them again, but there's really good evidence that it can be repeated. Now, with a stroke of perhaps genius, perhaps idiosyncratic lateral thinking, there was a suggestion from Michael Belkin, Professor Belkin in Israel, that if this is the mechanism by which this laser is working, maybe you don't actually need to directly hit the trabecular meshwork cells en face directly through the gonioscope. Maybe if you can just get enough energy into that same tissue, you would be able to have the same moderately inflammatory effect that would then have the same stimulatory effect that would then hopefully reset and repopulate the trabecular meshwork that we know is otherwise depopulated and loses trabecular meshwork cells at a faster rate in glaucoma than it does with natural aging. Maybe you could repopulate that trabecular meshwork with these messing cells, whether generated from the trabecular meshwork cells themselves or more likely from these stem cell niches that we know reside at Schwalbe's line and are the same site as the immediate post-laser cellular proliferation and increased DNA synthesis takes place, and there's good old histological evidence for that. And so what he did was to say, well, maybe we can just fire laser directly transsclerally, translimbally into this tissue because of where it sits, easily accessible, and did some proof of concept studies which way before the actual Belkin laser was developed, with a standard laser just firing it through the limbus to see whether it would work, and it did. And out of that initial sort of lateral thinking has grown the Belkin laser, which is now able to automate that process with gaze tracking software and track you around the limbus, and makes the process not just that much quicker, but also that I think that's much more reproducible and removing a lot of the operator variation in how it's carried out. It is worth noting that the energy delivery sits in the same sort of region of intensity versus time of tissue interaction as traditionally straight ahead delivered SLT does. That's very different from argon laser cooking laser trabeculoplasty with the photocoagulation, and pattern laser scanning photocoagulation and other forms sit in that same sort of region, that it's a thermal, because of the length of duration of the laser, because of the length of tissue interaction, it's changing the tissue, changing the nature of the tissue interaction. So it's a cooking thermal laser, and you've got to be careful about whether that. Clearly, those forms of laser have effect, because we know ALT is very effective, but they're not nearly as reproducible. And there's the concern that, or I have a concern that other forms of non-selective laser trabeculoplasty won't have any of the advantages of repeatability that and the safety margin that standard SLT and DSLT seems to have. So, the idea of transscleral laser without a gonioscopy lens. The first question that I asked when I got over the initial thought of that's insane, why would you do that, was, well, hang on a second, that's quite clever, because you've got some tissue scatter of that laser, and actually you may well be treating a sort of large area diffusely as the beam penetrates and is scattered by the very anterior sclera and peripheral cornea and the limbal tissues. And so the first step for them to do was, with their physicists, was to model the propagation of light through those tissues, to see how much scatter would be generated, to see what the energy density would be at the target tissue of interest, and make sure that there was enough energy being delivered and that it would be comparable to direct energy delivery through a gonioscopy lens. Now, the energy through a gonioscopy lens is not the same energy as hit the lens, because there are multiple interfaces through which that beam has to pass. It's got to pass through the interface with the air gonioscopy lens interface, and then the gonioscopy lens cornea interface, and then of course there's scatter through the tissues themselves. So there is some loss of intensity in standard SLT, and so there is also some scattering with this SLT, but the end result in terms of energy density at the tissue of interest is very similar. So the energy reaching that target trabecular meshwork is comparable. Of course, the proof of the pudding is in the eating, that does this actually have the same physiological effect on pressure, and that's the results of the GLORIA study, the randomized controlled trial that has finished recruitment, finished follow-up, and is now being written up, and for which some of the preliminary results have already been reported at the WGC, World Glaucoma Congress in Rome this summer. So differences in specifics of energy transmission with slightly different number of total spots gives us a total energy delivery reaching the trabecular meshwork that is very similar. And as I started off by saying, the choice of seeing physical bubbles from firing a laser through a gonioscope was really just to be able to prove that actually laser was doing something, so people felt comfortable they'd hit the right spot. There was there's no evidence that laser delivery requires that level of tissue disruption or interaction. In fact, the absence of bubbles at the trabecular meshwork is not necessarily an important sign for whether or not you're delivering it. And because of this is set delivery parameters, it's in that sense much more reproducible, and there's much less variability to worry about, I think. So the next step with SLT research is going to be the COAST trial. There's a low versus standard SLT randomization in the COAST, which has been funded by the National Eye Institute here in the US, a joint recruitment in the US and the UK, with Tony Riolini heading that up. It's an interesting study because it's a double randomization to low and normal power, and then a randomization to treat every year on an annual basis versus treat when necessary when the pressure increases. And I think it's going to be very exciting if this comes true. It's going to need an awful lot of laser if we find out that annual retreatment at low power is in fact better than just retreating when the pressure's high. Clearly, a direct SLT might be one way of achieving that if that's what we think ultimately we need to be doing on a regular basis. So that's a sort of whistle-stop tour of some of the evidence, a brief reference to some of the physics and the calculations behind the principles of Michael Belkin's original idea. And now's a great time to ask questions if you have any, but I won't be offended if you don't. Hello.
DSLT, does TM pigmentation play a role?
We did not see any relationship between TM pigmentation and response rates in the light trial because we recorded a clinical grading of TM pigmentation. And we couldn't find a relationship between TM pigmentation and results. Response to treatment, outcome, or hitting target. I suspect there is no, that there's a similar lack of relationship with DSLT, probably because of where the energy is arriving from, and it's there's enough pigment there in even unpigmented trabecular meshworks and very little pigmented trabecular meshworks to absorb the energy and still work. Photocoagulative trabeculoplasty like ALT relies on pigment, and unpigmented TM barely works. SLT, because of the nature of the tissue response that it's generating, does not require the same level of absorption. And though you don't see as much happening, you still get the same physiological response with standard SLT, and I suspect that's the case with DSLT. Hi.
Hi, Gus.
Great to see you.
Good to see you. Question, and I may
You've
be
always got the better ties.
Thank you. Maybe asking you to speculate. Mark Latina made a lot of what the end point should be for SLT. He was asking for champagne bubble. People treat to different levels, looking forward to dose response on SLT. But I won't be able to see anything with DSLT. Do you have any thoughts about whether we are looking for a dose response or whether there's one size fits all?
I always thought that Mark Latina's choice of the phrase champagne bubbles was a genius of marketing. And I did tell him that once. Because it sounds great. But I'm not convinced that we need that, even for standard SLT. There was a great pair of presentations once, which I don't think got into print, at the European Glaucoma Society meeting that were back-to-back. One was a case series, non-randomized, of low-power SLT with no bubbles, showing that it was really effective, and they were arguing we're over-treating. The next person had a case series of high-power SLT. They didn't know about each other. They were just back-to-back. High-power SLT, where you got a bubble every single shot, and they turned the wick right up, and they showed that it worked really well. What I took away from those pair of presentations, and I wish I'd taken details of them, was that it probably doesn't matter as much as we think we do, as long as we get some tissue reaction, because the tissue reaction is probably generated by even very little energy absorption. So I'm not worried about the fact that I can't see the tissue response because of where I'm treating it from, but I don't think it matters. Cool.
Okay.
Thank you very
great.
much.
Thank you, Gus. Thank you very much.